Welcome in subject mechanical system design. I am Professor A.P. Godke, delivering the lectures on mechanical system design subjects. So today we will see the topic of our unit number 6, that is optimum design. So in that we will see now today optimum design for redundant specification. So what is the need of optimum design for redundant specification, that we will discuss here first. So if it is not possible to develop the primary design equation to the point where the effect of all the secondary or subsidiary design equation and limit equation and specified parameters are included, then it is the case of redundant specification. Means whenever there is a limitation, or if we are not able to develop the primary design equation, or there is a limitation for a secondary or subsidiary design equation and a limit equation, and if specified parameters are included, then there is a need to go for the redundant specifications. So there are either excess number of limit equation or excess number of subsidiary design equation. So there are either excess number of limit equation or excess number of subsidiary design equation which cannot be combined properly with the primary design equation at one time. Then there will be the need of the optimum design for redundant specification. Also, if number of free variables are less than number of subsidiary design equation, then also we have to go for the optimum design with redundant specifications. So the optimum design procedure for redundant specification. So the steps are 1 to 6 are same as that of a normal specification. So what we have done in the normal specification, that already we know. So step number 1 to step number 6 are same as that of a normal specification. That is nothing but development of primary design equation, then development of subsidiary design equation, then development of limit equation, then combining the subsidiary design equation with the primary design equation. Then we get the new developed primary design equation. Then combining the limit equation with the new developed primary design equation. And after that, what are the parameters are required, that we are eliminating, and we'll get the normal specification. So for the redundant specification, step number 1 to 6 are common. Then what we have to do in redundant specification, that will be discussed here. So next, step number 7, combine the subsidiary design equation with the primary design equation by temporarily ignoring the some subsidiary design equation and or limit equation. This will convert the case of the redundant specification to the hypothetical case of normal specification and gives developed PDE also identify eliminated and related parameters. So in step number 7, what we have to do, we have to eliminate some of the subsidiary design equation and limit equations. So here we'll see one problem on it. A tensile bar of cross-sectional area at least 85 mm square and length of 200 mm and subjected to a constant load of 5000 Newton. Design a bar for minimum cost out of the following material. Assume factor of safety 2. So steel, aluminum alloy and magnesiums are the material. Mass density is given for the 3 material. Then material cost rupees per kg is given, and yield strength in megapascal is given. So the first step is to given data, basic configuration sketch and given parameters. So length is given 200 mm, that is a 0.2. So the force, axial force or tensile force is given as a 5000 Newton, that is 5 kilonewton. Then A minimum, that is a cross sectional area, is 85 mm square. Then L is the length of the bar, Fs is the factor of safety, and our objective is to minimize the cost of the material. The second one, second step is development of the primary design equation. So here Cm is equal to cost per unit mass of the bar material into the mass of the bar material. So that will be C into rho Al. Therefore, Cm is equal to C into rho into A into L into G if material cost is considered. So the equation A is called as a primary design equation. Then equation next will be the development or writing the subsidiary design equation. So that will be the tensile, since the tensile stress is included, sigma T is equal to force upon area. So that will be the simplest formula for the stress. Load upon area is the stress, force upon area. So equation B is called as a subsidiary design equation. Next one is writing of the limit equation, that is nothing but sigma T is less than or equal to SYT upon Fs, and A minimum should be less than or equal to the A. So equation C and equation D are called as a limit equation. And next we have a classification of the parameters, that is nothing but specified parameter, a limit parameter, and unspecified and unlimited parameters. So the functional requirement is effect parameter, geometric parameters, functional requirement parameter, geometric parameter, and material parameter. So here sigma T, Cm are the effect parameters, geometric parameters are the length and area, and material parameters are the density, then cost and ultimate stress. Then combining the subsidiary design equation with the primary design equation. So we will get the limit equation from equation A and B. There is no common unspecified and unlimited parameters in the primary design equation and subsidiary design equation. Hence, it is not possible to combine subsidiary design equation with the primary design equation by eliminating the unspecified and unlimited parameters. This is the case of redundant specification. So to solve such a type of the problem, it is necessary to ignore temporary either subsidiary design equation and corresponding limit equation, that is equation C, or limit equation on A, that is equation D, that is ignore equation B and equation C, or ignore equation number B. Therefore, number of free variables NF equal to 0 and number of subsidiary design equation NF is equal to 1. So here NF is less than NS, so it is the case of the redundant specification. So let us ignore equation number D, that is a limit equation on area. Assume A is the free variable and eliminate and hence convert the case of redundant specification to the hypothetical case of normal specification. So combine the SDE equation B with the primary design equation A by eliminating A. Therefore, A eliminated parameter. So Cm is equal to rho C into rho into A into L. So here A will be eliminated in the form of F upon sigma T. So that Cm will be equal to C rho FL upon sigma T. So putting the value of force and length, we'll get the one equation E. So the equation E is called as a newly developed primary design equation by eliminating the parameter A by secondary or subsidiary design equation B. So sigma T is known as a related parameter here. So combining the limit equation with the developed primary design equation, from developed primary design equation, we have a Cm is directly proportional to the sigma T. So for minimizing the Cm, the parameters sigma T should be placed at its upper limit. So SYT upon Fs. So equation E becomes Cm is equal to 1000 into C into rho upon SYT upon Fs. So this will give you a minimizing equation for the minimizing of the cost, 2000 into C into rho upon SYT. So determination of the feasible range of the optimum design quantity. So from equation F, the lower limit on the material cost for the different materials are as follows. So putting the value, all the values, you will get the for steel material Cm1 and for aluminum material Cm2 and for aluminum material, for magnesium material Cm3. So the feasible range of optimum design quantity cost will be 1.84 Rs for steel, 3.84 Rs for aluminum alloy and 6.72 RS for magnesium alloy. Taking log on both sides, we will convert into the digit, that is 0.2662, 0.5843 and 0.8274. Then variation of optimum design quantity with respect to the eliminated parameters are, in this case, we are replace the related parameter sigma t in primary design equation by eliminated parameter A by using secondary design equation. So here our secondary design equation, Cm is equal to 1000 C rho upon F upon A. So that will be 0.2 C rho A. So taking log on both sides, you will get this equation in the form of C plus Mx, that is Y is equal to Mx plus C from. So we are developing the same equation for three materials, that is for steel, for aluminum alloy and for magnesium alloy. Then plot of log to the base 10 Cm against log to the base 10 area. Means we are plotting the minimizing the cost against the minimizing the against the area. Therefore, optimum design parameters for minimizing the cost is the material selected, log to the base 10 Cm is equal to 4.38 plus log to the base 10 area. So here area will be A minimum. So that will be 85 into 10 raised to minus 6. So from this you will get the first cost, that is a Cm1 is equal to 2.0389 RS. So Cm1 is equal to 2.04 RS. So for normal specification, and we will take the comparison what is meant by normal specification and what is meant by redundant specification. So here in this case, it is always possible to combine all the subsidiary design equation with primary design equation without eliminating or ignoring the limited or specified parameter. So this is the simplest case of optimum design. So the number of free variables are greater than or equal to number of subsidiary design equation. While in case of redundant specification, in this case, there are either excess number of limit equation or excess number of subsidiary design equation, which cannot be combined properly with primary design equation at one time. In this is the case of, this is the complex case of optimum design. So the number of free variables are less than with the number of subsidiary design equation. So it will be greater than or equal to number of subsidiary design equation. This will be just less than, number of free variables are less than the subsidiary design equations. So thank you for watching the redundant specification problems.